Swayam Prabha. Digital India. Educated India.
We have seen how we can calculate approximately the stress in a plate which is simply supported at the edges and subjected to uniformly distributed pressure loading P. Let us consider today if we have the plate simply supported at the edges and loaded by a concentrated force at its center. So, we consider the plate to be like this. It has let us consider that this load P, to begin with, it is distributed over an area of radius A at the center, and obviously we are trying to talk about B is very large compared to the outer radius B. We will try to see when this A shrinks to 0, then we will get the case of the concentrated loading. So, let us calculate the stresses for this case by taking the approximate approach that we have considered for the simply supported plate with uniformly distributed loading. So, now if I try to consider this is 1/2 of the plate, this is the outer circle and this is the inner circle. Now, this is the point O. We consider that all along this diameter there will be some bending moment acting whose intensity, let us say, is m. So, that is m per unit length of this diameter. Now, if we consider the reaction at the supports, which is going to be uniformly distributed and it will have some intensity, that intensity can be very easily found out. That distributed force would have a center somewhere there. Let us consider that it is lying on this radii and at a point O. Similarly, the force P, which is distributed over this circle, and therefore, P by 2 will be acting over this semicircle, will have the centroid somewhere there, which is B, let us say, and therefore, we can very easily establish that this OA is equal to nothing but 2B by pi. OA, that distance is 2B by pi, and OB is nothing but 4A by 3 pi. This intensity of bending moment, let us represent it by m everywhere. The loading which is uniformly distributed over this small circle, the intensity of this loading, let us just say P, sorry, I am sorry about that. Let us consider that the reaction force which is all over this boundary is equal to P per unit length. Then in that case, we can write P into 2 pi B is equal to P. Better to will better represent this reaction at this point to be R rather than P, because P let us reserve for uniform pressure. So, therefore, this is R into 2 pi B equal to P. So, we get that intensity of the loading. Similarly, we can also find out P, which is the intensity over the smaller circle. It is going to be nothing but P by pi A square. So, both these informations are available. Now, we calculate we consider the moment balance. So, this moment balance will now take up about the diameter, let us say that this CD. So, if we take the moment balance, about CD, then we have M acting all over the distance CD, which is of length equal to 2b. So, we will have anticlockwise moment of magnitude M into 2b. We have this load which is acting over this semicircle, its magnitude is P by 2 and its moment arm is 4a by 3 pi. So, therefore, this moment is again it is acting downward. So, therefore, it is acting downward. So, therefore, we will have again anti-clockwise moment. So, the moment is nothing but 4a by 3 pi minus the load which is acting over this boundary. It is also sum total is nothing but P by 2, which can be obtained by considering that R by 2, it is R into pi b is going to be P by 2. So, therefore, that P by 2 is the force which is acting upward. So, P by 2 and its moment arm is OA, which is 2b by pi. So, 2b by pi equal to 0. So, that gives us the moment balance, and therefore, M 2b is equal to Pb by pi minus 2 Pa by 3 pi. So, simplifying we get this, and now we can write therefore M is equal to P by 2 pi 1 minus 2a by 3b. So, that is the moment per unit length of CD. And now, if you want to calculate the stress will be available by considering that maximum stress is nothing but 6m by h square. So, if we now try to calculate sigma max, it is 6m by h square. So, therefore, 2 will cancel. So, we will have 3p by pi h square into 1 minus 2a by 3b. So, that is the magnitude of the stress. And we are looking for a case when the radius of this circle is 0, that will really lead to the concentrated loading at the center of the plate. So, therefore, if we do that, if we just try to consider now A equal to 0, so if we now put A equal to 0, we will have sigma max is equal to 3p by pi h square. So, that is the maximum stress which is going to occur at the bottom fiber. It is going to be tensile stress, and if it is at the top fiber, it is going to be compressive stress. You might be interested in trying to know what is the exact value of the stress if we go rigorously for the analysis. Then in that case, this maximum stress, so exact answer is nothing but 3 into 1 plus nu 2 pi h square into p one plus nu plus ln b by a minus 1 minus nu 1 plus nu a square by 4 b square. So, that is the exact expression. So, you can see that this is what when we have a and b both are non-zero, and that compares to this exact expression like this. There is some difference, but then for approximate calculation one can make use of the formula which is derived approximately following the steps that I have talked about just now. So, this is about the circular plate. You can go on doing similar calculations for the rectangular and square plates. So, let us try to consider the case of a rectangular plate, and from the rectangular plate we can get the answer for a square plate. So, the plate is shown here. The dimensions, let us consider that the height is a and this width is b, and it is subjected to uniformly distributed load the plate is simply supported at its outer boundary and the pressure loading is P. Obviously, the reaction over the boundary is not going to be uniform as in the case of circular plate. Here the center of loading is exactly at the center of the plate, and this point, these middle points of the sides, they are closest to the center of gravity, and therefore, what you find is that reaction is going to be non-uniform and it is going to vary along the boundary. If we just assume that the reaction forces at the boundary is going to vary linearly, then in that case we can consider that the reaction is going to be the maximum at the center of the side. So, therefore, the reaction forces are going to have a distribution like this over this boundary. Similarly, we are also going to see some distribution of the reaction force over this side, and similar thing will be repeated for the other two sides. We are not really going to find out the maximum of this distributed loading, but then what we just assume is that it is going to vary linearly. Let us consider, let us indicate this plate by A, B, C, D, and let us say the total reaction at the edge AD is given by R1, and obviously its centroid is going to be here. Similarly, for the side AB, the total reaction is equal to R2, and therefore, we are going to have reaction here is R1, reaction there is R2. Now, if we consider half of the plate, let us take a diagonal section. We just cut the plate into two along this line BD. So, if we do that, then we will have shear forces acting on this diagonal, plus we are going to see the bending moment. Let us say that this bending moment is uniformly distributed all over with some intensity, let us say that is equal to m. So, what we have? We have a triangular plate where we have some shear forces acting over this line BD, and then we have force, reaction force R1 acting vertically upward. This is also R2 is acting vertically upward, and there will be some reaction forces over BD which can be vertically upward or downward. We are not really concerned about it. Now, the external loading, which is uniformly distributed pressure over the triangle ABD, it is going to have its center. So, it is going to be, if we drop a normal here on this diagonal, so at 1/3 of the height somewhere here, we are going to get the center of the loading. So, therefore, this ON is the distance of this CG of the distributed pressure. Now, let us consider that this OA is the height which can be represented. We can consider that to be, we can also calculate that, we need not actually write it explicitly. So, let us first of all write the force equilibrium. So, if we consider the force equilibrium herein, that sum of R1 and R2 must be equal to, or twice R1 plus twice R2 must be equal to the external loading. So, that is the equilibrium of the whole plate. So, therefore, if I write the equilibrium of the whole plate in the vertical direction, then we are going to get 2 R1 plus R2, that is equal to total downward load, which is P times AB. Therefore, we have R1 plus R2 is equal to PAB by 2. So, that is from the whole plate we get that equation. Now, we can calculate this height OA. OA, we can consider that by considering the fact that this area of the triangle is nothing but AB by 2. So, therefore, that is the area of the triangle. Now, if we consider area of this triangle, again it should be equal to half dB into OA, and dB is nothing but square root A square plus B square. So, therefore, from that relationship we can calculate the height OA. So, OA is nothing but area of the triangle divided by length dB, which is nothing but A square plus B square, and that half into that will give us now 2 here. So, therefore, that gives the value, and therefore, this height OA is nothing but square root A square plus B square. So, that is the height. Now, we go for considering the equilibrium about the line dB. So, if we now consider the equilibrium, so we will have anticlockwise moment, which is m is the intensity multiplied by the total length is A square plus B square of the diagonal dB. So, therefore, that is the total moment in the anticlockwise direction. It is counterbalanced by the moment produced by R1 about this line dB, R2 about this line, and at the same time distributed pressure acting downward through the point N. So, therefore, we can now write that this R1 and R2, obviously you see that this CG is going to be, CG is here, that CG height is going to be nothing but half of this height. Similarly, CG of this R1 is going to have height which is again going to be half of this height. So, therefore, for both the cases we have height equal to nothing but h by 2. So, this is nothing but this OA by 2. So, therefore, this is OA by 2. So, also this is also equal to OA by 2. So, I would like to repeat that. So, therefore, we have R1 plus R2 OA by 2, that is what is acting in the clockwise direction, and this load is nothing but P AB by 2, because P is the intensity and area is AB by 2. So, therefore, P AB by 2 is the total downward load and its distance is ON, which is 1/3 of OA. So, therefore, that is the moment, and this moment is going to be downward, and hence it is anti-clockwise. So, therefore, this gives us the moment equilibrium about dB, and finally, if we substitute the value of R1 and R2, R1 plus R2 is nothing but PAB by 2. So, we have PAB by 2 AB by 2 into A square plus B square minus P AB by 2 into AB, this is 3 A square plus B square. So, that is the value, and once you substitute, you know that PAB is nothing but, if you consider the total pressure is equal to W, therefore, we can write now this is nothing but W AB. So, it simplifies to 12 square root A square plus B square. So, that is the, and this is the total load due to P, and hence M, intensity per unit unit length dB is nothing but WAB by A square plus B square. So, that is the moment per unit length, and obviously, you see that unit is also balanced, because this is going to give us meter square, this is going to cancel with meter square, but then we can write this thing as Newton meter per meter. So, now if I consider square plate, so for A equal to B, we have M equal to W by 24, and therefore, sigma maximum is equal to 6 W by 4 by H square, and this is nothing but P by 4 A square by H square. So, again it is a good approximation. So, you can calculate by this simple approach the approximate stress acting at the, and it is going to be really critical at the center, and therefore, you can calculate that critical at the critical location what is the stress acting. Now, we would like to consider some problem solving. We have taken up number of cases. So, let us now consider some applications so as to consolidate whatever we have derived so far. So, let us now consider one example on the design of a plate. It is a thick plate of uniform height h or thickness h. Its diameter is 4064 millimeter. The total load which is uniformly distributed, which is given by 1,81,440 Newton. That means it specified that the design stress for the plate is 56.24 Newton per millimeter square, and E for the material 182.78 GPa, it is steel, and Poisson's ratio is 0.3. What is needed is that calculate the height h and or thickness h and the maximum deflection of the plate. So, therefore, that is the problem. So, let us now go for calculations, and in fact, this is going to be direct application of the formula that we have derived. So, now let us look at the solution. If we just take the expressions, that maximum stress in the case of a circular plate subjected to uniform loading and simply supported at the edges, the maximum stress was at the center and its magnitude was 3 by 8, 3 plus nu p a square by h square. So, herein what is given is that you have to get P from the total load and the diameter, and A is already specified, and sigma maximum, it happens to be limited by the design stress, and therefore, only unknown is H. So, you can calculate it. So, now we can try to plug in the values. So, we have this thing as 56.24, and that is equal to 3 by 8, and this 3 plus 0.3, it gives us 3.3, and P is nothing but total load capital P, so 1,81,044 Newton, and now if we divide by the area, which is nothing but pi d by 2 whole square. So, that gives us the pressure in Newton per millimeter square, and A square is 4064 by 2 whole square divided by h square. So, that is simple substitution, and here in this cancels with this one, and therefore, the calculations become simple. And if you now calculate the thickness comes out to be 35.65 millimeter. So, the thickness of the plate has got to be this much. Now, second thing, we have to calculate the maximum deflection of the plate, and the deflection is obtainable from the pressure, Poisson's ratio, modulus of elasticity, and also the dimension of the plate. So, if we do that, first of all, the formula that we had derived for the maximum deflection, it was right at the center of a circular plate. So, that maximum deflection, if we write W maximum is equal to 5 plus nu by 64 d 1 plus nu p a raised to the power 4. This d is nothing but modulus of rigidity, and therefore, we should calculate this value, rest of the values are all given. So, therefore, let us now calculate this d. So, if we consider this d is nothing but Eh cube by 12 into 1 minus nu square. So, it is different from that of a plate, and its value is Eh cube by 12 into 1 minus nu square. So, let us substitute the value here, 182.78. If we want to keep it in Newton per millimeter square unit, then it will be simply 10 to the power 3 and this is 35.65 cube divided by 12, 1 minus 0.35 square, and this gives us 7,58,000 to 81.786 10 to the power 3. It is in Newton millimeter units. If we now substitute the values, we have 5 plus 0.3 for nu, and this P is given by total load divided by the area, which is pi r square, and again R is nothing but this raised to the power 4, and we have 64. D value is given here, 1 plus nu is 1 plus 0.3. So, once we simplify this, it gives us value to be 20 millimeter. Now, we would like to consider another example wherein the same plate subjected to the same total load, but then it has a circular cutout at the center of some radius, which is 1/4 of the outer radius. So, the problem is shown here. This is the plate, the cutout at the center is of radius A and outer radius is B. The load is uniformly distributed. Total load out of this uniform distribution is 181,440 Newton, and as I said that this inner radius is 1/4 of the outer radius. Now, let us see what happens to the maximum stress and the deflection. So, these are the two things to be calculated. To solve this problem, we do not want to go for deriving the formula. We will make use of the results which are available in the tabular form, take the data directly from the table and do the calculations. In order to make use of the tables that we have considered in our earlier lecture, we need the value of the ratio B by A. So, if we have the ratio B by A, in this case is 4, then the constants which are associated with the calculation of the stress and deflection. So, this is the constant which is associated with the calculation of stress. So, therefore, this is B by A is equal to 4, and therefore, consulting the table we get the constant K as 2.08, and similarly the other constant which is associated is 0.830. P is now total load divided by pi by 4, 4064 square, that is B square minus 1016 square. So, that gives us value equal to 0.01492 Newton millimeter square. The maximum stress is given by this formula, small k into P B square by h square. So, here h is nothing but 35.65 that we have got in the earlier case. So, that we have to make use of, and we have to calculate this maximum stress. So, therefore, this is equal to 2.08 into 0.01492. B square is nothing but 2032, and the height of the plate is 35.65. So, B by h square. So, if we do that, it gives us a value of 100.88 Newton per millimeter square. Remember, the value in the earlier case, we had the maximum stress was 56.24 Newton per millimeter square. Just by having a hole at the center of radius 1/4 of the outer radius, we get the stress amplified by almost 2 times. So, that is the amplification in the stress. Now, let us see the value of the maximum deflection. So, if we calculate the maximum deflection, again it is given by the standard formula, delta maximum, or it will be W maximum is equal to K1 into P B4 by EH cube. So, W maximum is K1P B4 by EH cube. So, if I substitute the value, that is the value of B, and this is the value of E, 182.7 into 10 to the power 3, and this is 35.65 cube, and on simplification we get this thing as 25.5 millimeter. The deflection in the earlier case we had only 20 millimeter, now the deflection is increased to 25.5 millimeter. So, this is a very simple way to go about finding out the deflection and the maximum stress, provided the configuration falls within the cases which are tabulated. Now, we will try to consider a different problem. It is not necessary that we have to have uniform thickness, and the formula that we have derived, they can be applied. Sometimes it is also possible to apply to situations which are different. Consider, for example, in many cases in applications you find that a plate is made up of one plate of uniform thickness, and it is welded to a grillage at the bottom or at the top, and therefore, such cases are also treated like uniformly thick plate, and calculations can be done. So, we would like to show one particular case. The problem is like this: a 6096 millimeter diameter nuclear core support plate is composed of a solid plate of 50.8 millimeter thickness. To this plate, an orthogonal grillage consisting of 254 millimeter deep and 50.8 millimeter wide waves are integrally welded. The grillage dimensions are 254 millimeter deep, 50.8 wide, waves are of 250 millimeter dimensions. It supports uniformly spaced nuclear fuel elements of total weight of 14,51,520 Newton, assuming the structure to act as a simply supported plate with uniform edge reactions. Determine the flexural rigidity D, bending stress at the top of the flat cover and bending stress at the bottom of the grillage of the weld. So, these are the things to be calculated. Just to have a picture of the configuration, it is like this, that you have a plate and there are grillage like this. You have stiffener of uniformly thick plate and these are spaced at a particular pitch distance. Similarly, you have cross grillage also, they are plates of this much height and this thickness. So, this sort of grillage. So, think of it that this plate is placed on top of this grillage and they are welded everywhere. So, that becomes a monolithic structure and this sort of problem can be also solved by considering the formula that we have derived. So, I will give you the procedure to solve it. So, if we look into this problem, what you have is that you have a plate of thickness 50.8 millimeter and then we have grillage of height 250 millimeter and thickness is equal to 50.8 millimeters and this pitch is 254 millimeter. So, now if you try to consider a portion of the plate which is 254 millimeter, let us say, then it looks like this. The section of the plate is going to look like a T. Now, this becomes the dimension of the section rather than uniformly thick plate and we can do the calculations considering I for this section. Other data are that P is equal to 14,51,520 Newton, that is the load, total load acting on the top, and pitch is of course 254 millimeter and thickness of the basic plate is 50.8 millimeter. Now, the problems to be solved are what is the D, value of modulus of rigidity, maximum stress at the top, maximum stress at the bottom. So, before we do that, it is necessary to calculate the I for this section. You treat it as if this is the section of the plate and therefore, we can now calculate the location of the CG. All the dimensions are known, we can calculate this CG location of this section and I would like to just be brief here. So, if we calculate the CG distance y bar, that is you can calculate by considering the moment of this portion about this base, moment of this portion about this base and that divided by the total area of these two segments. If we do, that will give us y bar as 101.6 millimeter. So, therefore, this CG is located at a distance of 101.6 millimeter from the top. Now, if we know that, I can now calculate the moment of inertia of this section about Ixx. So, if we calculate Ixx, we can now consider this segment which is of dimensions 254, height 50.8. So, therefore, we will have the moment about its own CG parallel to x axis is 254 into 50.8 cube by 12. So, that is the moment about the axis passing through this point parallel to x. Then we apply the parallel axis theorem. So, therefore, it is 254 multiplied by 50.8 multiplied by, now the distance, this distance is 101.6 and this is nothing but 50.8 by 2. So, therefore, if we now take the difference 101.6 minus 25.4, that is the distance between the two CG. So, therefore, this is the contribution of the parallel axis theorem. Similarly, the wave we can consider now it is of thickness 50.8, its height is 254. So, therefore, BH cube by 12, that gives us the moment of inertia about the CG of this wave somewhere there. And then if we apply the parallel axis theorem, so 50.8, 254 is the area, and the distance is nothing but this total distance. We can consider that if I consider this total distance is going to be 50.8 plus half of this height, which is 127. So, that total gives us 177.8 minus 101.6 square. So, therefore, that gives us the contribution of the parallel axis theorem. So, on simplification, we will simply write I rather than Ixx. This is nothing but 22,198 into 10 to the power of 4 millimeter raised to the power 4. So, that is the moment of inertia. Now, this d is nothing but EI by P, pitch distance. So, it is moment of inertia over unit length, and we are considering a pitch distance of 254. So, therefore, now we can find out this d. So, therefore, this is E into 22,198 into 10 to the power of 4 divided by 254. So, this gives us 873.976 into 10 to the power of 3 E, and it is in Newton millimeter units. So, we have to keep everything in Newton millimeter. So, that is the value of d. Now, how do you calculate the stress at the top and bottom? Now, we can apply the formula that stress is nothing but m maximum moment by I into y1 distance of the fiber. So, therefore, what it means is that if you are interested in calculating the stress at the top, what you need to do is that you find out the maximum moment and that divided by I multiplied by y, that will give us the stress. Now, obviously, this I that we have calculated, it is for a pitch length of 254, and this I should be calculated per unit length. So, therefore, if we can write now, this maximum stress for this problem is going to be at the top is nothing but m this I per unit length. So, therefore, I by P into y1, because this moment is given per unit length. So, therefore, this has got to be also per unit length. So, sigma maximum is equal to m by I by P into y1. So, if you are calculating the stress at the top fiber, you must think of the distance y1 of the top fiber from the centroidal location, and this m is moment per unit length. So, this I is also to be expressed as moment of inertia per unit length. So, now we can write the value of the moment is nothing but 1 by 16 P s square into 3 plus nu. So, therefore, we have 3 plus nu into 1 by 16 pressure distribution, which is capital P by pi a square. So, that is the small p, and that multiplied by a square, that is the expression for the moment per unit length. And now, we can write y1 is nothing but y bar, and this I by P will be I by P. So, if we now substitute the value, it is 3.3, and this load is equal to 145.1520 by pi a square we can cancel this a square with this a square. So, we need not substitute, and this is 101.6 millimeter, and this value we have 221.98 10 to the power of 4, and this P is nothing but 254. So, these are the values, and once you calculate this, this simplifies to minus 11.078 Newton per millimeter square. So, this is the stress at the top fiber. If the stress at the top fiber is this, there is a linear variation. So, you have linear variation of stress from the top to the bottom in the case of simple bending, and therefore, you can calculate the stress at the bottom fiber. This is nothing but 11.078 divided by 101.6 multiplied by, it is 50.8 plus 254 minus 101.6. This gives you value equal to 22.156 Newton per millimeter square. You expect naturally the plate to be subjected to tensile stresses at the bottom under the action of the load at the top, and compressive stresses to come up at the top. So, therefore, we have got those stresses. So, you can solve the problem of this type where the thickness is not uniform by following procedure like this. You can consider problems for solving yourself. So, look into the problem of this type. A clamp plate of diameter A is subjected to uniform pressure loading P. Determine the radial location for which sigma r, which is nothing but sigma 1 equal to 0 and sigma theta equal to sigma 2 at the bottom of the is 0 at the bottom of the plate. So, therefore, determine the location where sigma 1 is going to be 0 and sigma 2 is going to be 0. Obviously, a plate which is subjected to loading at the top, you know that for a clamp plate the stress varies from positive to negative. So, there is a 0 somewhere in between. So, those are the locations to be determined. So, answer is given here. Similarly, you have a plate here which is subjected to bending moment M1A per unit length at the inner edge, M1B per unit length at the outer edge. Determine the variation of M1 and M2 from R equal to A to R equal to B under the condition when M1A equal to 0. So, it is a plate which is subjected to uniform bending moment at the outer circumference. Find out the variation of the bending moment in the radial and circumferential direction. Similarly, you can consider a plate which is loaded like this. The radii of the plate is r equal to x equal to A to x equal to B. The loading at the outer edge is P per unit length and loading at the inner edge is Q per unit length. For this place, write the boundary conditions. For a plate like this, wherein it is supported at the edges and distributed loaded over the annular area, which is from x is equal to A to x is equal to B, determine the variation of moments M1 and deflection W for the plate shown. So, you can follow the steps that we have given you earlier and get the answers to these problems.